So the problem we're trying to solve was the fact that the same characteristics of tires that make them so useful make them a large problem for disposing of them because they're so resilient. They sit around in landfills and are a large home for pests like rats and a breeding ground for mosquitoes. So, as well as the fact that tires are made of hydrocarbons, and so there's a large waste of usable chemicals there. So our solution was a pyrolysis to convert the tires into chemicals like limonene and and carbon, solid carbon. So our main objective was to design a experimental setup that fit inside a fume hood in order to capture any escaped gases and such, as well as to increase the control over the experiment. The main thing we were looking at was the composition of our products and where the sulfur contained in tires was going. We looked a little bit at sulfur separation techniques, but as we didn't get too much data on our sulfur content, we don't have very much there. So pyrolysis is an anaerobic thermal decomposition. It produces a bio-oil made up of multiple different chemicals like limonene and solid charcoal and combustible gases. Alternatives would be civil engineering projects like backfill for roads and such. You could also use gasification to dispose of tires and liquefaction to dispose of tires and capture their chemicals. Both of these were a little bit more in depth than pyrolysis. Gasification requiring some more steps in order to convert more of the solid product into the gas, and liquefaction, the same thing, in order to move more of the products into the liquid product.
So the first step to do this, we make a bench scale model that could fill our needs. Like you mentioned, it needed to be in a fume hood because we don't have anything to process the gas yet. We were just looking at the liquid sample in this experiment, and we wanted to have a system where we could control different variables and see how that impacted our setup. Whoops. Okay, so to do this, we used a tube furnace that supplied the heat for pyrolysis. The reaction occurred in this tube right here. It's made out of quartz to withstand high temperatures, and the rubber was placed into either this large metal boat or this smaller glass boat to contain it and make it easy to insert and remove the rubber from the reaction tube. So after the pyrolysis occurred, the products went through here. Nitrogen was fed into this arm here, and the nitrogen swept the product down to the cold trap here. This is the tube that goes in the cold trap. And we had an iced water bath, and what can condenses here, and the non-condensable gas comes up here and goes out the gas trap, which we filled with oil, vacuum oils. And the purpose of the gas trap was to avoid oxygen, or to prevent oxygen from entering the system. And that's also why we use nitrogen, because if you have oxygen in the system, you're going to be burning the tires instead of pyrolyzing tires. And we needed insulation, because if you didn't insulate between basically the end of the tube furnace until the cold trap, the gas would condense in that glassware, and it's really hard to remove that when it's caked to the side of the glassware and not at the bottom of the cold furnace, the cold trap, where you can just easily collect it. So here's a key idea of the system. To do the experiment, we put the sample in here, heat it up. When we're done, we just we take and remove that tube and collect the sample. We store it in a freezer to prevent the volatiles from evaporating off. And I think that's all covered. Wait, sorry, I'm pressing the button. When we were doing the experiment, we looked at how a few of the variables impacted the results. Both the temperature variation of the furnace, what the maximum temperature we took it to, and the sample size. We were wondering if that would affect how much repolymerization there was, because first the pyrolysis will cause the rubber, which is mainly polyisoprene, to depolymerize. And if it's still hot, it can repolymerize back into monoterpenes, polyterpenes, and anything in between. And we found that sample size had very little impact, and the higher we heated the sample, the more product we got, but the more of the product that repolymerized as well. Insulation was necessary. I already discussed that, to keep the product from prematurely condensing. And nitrogen flow rate was also pretty interesting. If we varied it from 0 to about 10 milliliters per second. If there was no flow rate, then the product would all condense right in here. It just never got to the cold trap because it needed to be pushed there. And then also, if we had the nitrogen flow rate really high, we're introducing cold gas, and that would cause it to prematurely condense in the glassware as well. So we had a moderately low flow rate of about 1 to 2 milliliters per second, and that was enough to move the gas to the cold trap, but not prematurely condense it.
Alright, so another goal of our project was to analyze the liquid tire that we got from our pyrolysis reaction. One of the most important products was limonene, which is a monoterpene or 2 isoprene units. The first analysis we used was gas chromatography mass spectroscopy. You can see the gas chromatography here and then mass spectroscopy here. This was we ran 2 different samples of 2 different sizes were our main products. We had run number 7, which was in our small boat that you guys saw earlier, and that contained about 2 grams of tire rubber, and run number 9, which contained about 28 grams of tire rubber, so a factor greater. This run number 7 sample, this largest peak right here, zooming in on it to look at the mass spec data in this region, we saw that this mass spec data corresponded almost exactly to a limonene GCMS that we also ran. Further, this is we also ran a microgram tire, so we took just a small portion of our tire rubber, pyrolyzed it, and fed it directly into the GCMS to get an overall spectrum of our product. So overall, what we saw, what we could actually obtain from our tire, was various different carbon compounds, mainly aromatic carbons, such as pentadiene, xylene, the DL-limonene, which we were talking about, which is our most important product, and then also different polymer terpenes is what we expected. So we saw different various groups if you come back here. So and since this is run number 7, we saw this group here, and then we see this larger group here. In our full tire analysis, we saw several other groups further on that we expect to be larger terpene samples. So 3 isoprene units and 4 isoprene units, which corresponds with 15 carbons and 20 carbons. So our actual product, run number 7 and run number 9, it was important to us that these samples be the same, because if you scale up how much products you have for our final composition or economic analysis, we wanted to make sure that our bench scale design actually would relate to what we would see if we ran a full design. So we wanted to see if we actually increased the amount of tire in our boats, if that actually had an effect on the sort of products we were getting. And Fortunately, it did not, that the products we were getting in the run number 7 sample was similar to the 2 products we got in run number 9 sample. The 2 run number 9 samples were simply different. In the second one was more viscous. It was collected higher up in the sample, in the cold trap, and contained the monoterpene, or the larger terpene peaks, whereas run number 9 and run number 7 mainly just contained the monoterpene peak. In addition to GCMS, we also ran an NMR on our run number 7 sample. As you can see in this, we have here just a limonene standard for an NMR, and this is our full NMR for our run number 7 sample. You can see that the main peaks that are in limonene are also the main peaks that you can see in our NMR, further suggesting that we do contain a large amount of limonene in our product. In addition, there is sulfur contained in vulcanized tire rubber. So we wanted to test how much sulfur content we had, because sulfur is an impurity and we need to get rid of it in order for our process to be economically viable. So we sent our samples into a lab to perform elemental sulfur techniques. We saw that the 2 samples contained about 0.5% sulfur, and we also did a run on unreacted and reacted tire and saw that the sulfur did primarily stay in the tire. However, there was still sulfur in our liquid product, so that sulfur does need to be eventually removed or limited in order to increase our economic profit.
This is a full-scale plant design that we came up with, and so for pre-processing, it goes through bead removal, which extracts the inner lining of metal inside the tire, and it is shredded and goes through a magnetic separator, which will extract all the steel from the inside the tire. That way we'll have just purely shredded tire feeding into the pyrolysis machine. And so it's fed into here, and we use an auger to push the tire through the pyrolysis, and the carbon black is collected here at the bottom. And the gas product will feed into a condenser, which can then be processed in the distillation column. And here's an overview of our economic analysis. We based our numbers off of being able to process 30 tons of tire per day, and we see that we would be making a profit of about $12,700 with a capital cost of $900,000 to start up the plant. We decided to locate the plant in Toledo, Washington. That way it's within 100 miles of 2 major cities, Seattle and Portland. And this will allow us to easily get shipping from different sites, and it would be easy for us to have a constant supply of tires. And if we exhaust the supply from those 2 cities, Vancouver, British Columbia is 200 miles away, Spokane, Washington is 350 miles away, and Boise is 500 miles away. So they're all relatively close to this location. And another thing we had to take into account was whether we wanted to purchase pre-shredded tires or use whole tires and shred them ourselves. The advantage of getting pre-shredded tires is that we wouldn't have to do any of the pre-treatments, and we could just feed it directly into the pyrolysis. Some disadvantages is that we would have a higher upfront cost of having to pay another company to do the shredding for us rather than doing it at the plant site. And also, since we would be able to recycle the metal, would not be that would come out of the daily profits for us. So for labor, we would have a 3-man crew working on shipment and pre-treatment, then having somebody monitoring the pyrolysis and the distillation column. Then there would be a head manager to oversee the plant and make sure everything's running smoothly, work out shipment details and stuff like that. Then having another three-man crew on post-treatment and packaging. Then we would have 3 process engineers on site to make sure that the systems are optimized and conduct improvements for the plant. And as I talked about before, we would be making nearly $13,000 per day with our current design, but these numbers are based on some stipulations. We're assuming that we are able to actually extract the limonene through distillation. Further research needs to be done with whether that's possible to extract from the fuel oil, and so that would affect our numbers. And if we decide to use pre-shred tires, then we would not be extracting the steel, and that would come out of our profits. And the shipping costs also depends on the distance. We based our numbers off of being able to ship it from Toledo or Seattle to Toledo, and any additional distance would increase the costs.
So some future work still needs to be done, such as larger scale testing of our tire, removing sulfur, and testing different setups of our final glassware. In conclusion, we talked to you guys about our fume hood setup, our composition of our tire, and the final economic analysis. And thank you, and are there any questions?